Alright, in the last part of Lab 1-5B, we're going to return to the diffraction grating, but this time we're going to use white light. Now in an earlier lab in this course, you saw the effects that did. It produced a colored spectrum of the white light from blue out to red. And we're going to see that again today. But today we're going to use the formulas and the equations that you understand now for diffraction grating to actually calculate the range of wavelengths that we can see coming through that diffraction grating. We're going to collimate that white light just like we did before with a little index card so that we'll block out all that stray light around the sides so that we'll be able to see that very dim colored spectrum. And we're going to have to be careful to line up our diffraction grating and orient it so it's not skewed one side or the other, just like we had to do for when we measured with the laser pointers. In fact, we can use the laser pointer to help us get that diffraction grating squared up. And then when we shine the white light through it, we'll see that the measurements on either side of the diffraction grating are pretty much balanced as they should be. Okay, let's go look at that equipment. So as you can see, we've got the little white index card that's serving as a collimator wrapped around our white flashlight. It's sending light over to our diffraction grating, and as I suggested, we're using the laser pointer to help us square up the diffraction grating so that it's not turned sideways over here. We've got our diffraction grating exactly 1 meter away from our whiteboard. And now let me dim the lights, and I'm going to have to really slow the camera speed, shutter speed down here so that you can see the colored spectrum in the dark. So as you can see, we have the white light from the flashlight shining through the diffraction grating. And you can see the shadow of that diffraction grating on the wall. And to the left and the right, you can see the colored spectrum. You can see my laser pointer dots are also down there. The wavelength of the laser pointer is also in the right spot with respect to the white light, correct? The color? See the red? Alright, so I'm going to go and place some marks on the board corresponding to the locations of the far left of the blue and the far right of the red on both the left and the right side patterns of the diffraction grating. So here are the marks that I made. I found an interesting thing that as I got down here, I was able to look at the reflection of the colors coming off of this shiny surface of the whiteboard, which actually was much more sensitive on my eyes than actually seeing the colors on the board, even with the camera. So I was able to do some very good marks, and if I measure the distance from the center over to here, I get about 41 centimeters for the blue end of the spectrum, and the red end is out past 100 centimeters, so I'm going to just measure it from the 41 out to about 63, so that would be 104. So I have 41 centimeters for this distance and 104 centimeters for that distance. And I'll make the same measurement on the other side. So I took the measurements from both the violet and the red ends of the spectrum on both sides of the diffraction pattern, and I got about 104 centimeters out there on both sides, and on the inside I got about 39 centimeters on one side and 41 on the other, so we'll average it and call it 40. Now we can use our diffraction formulas that we know to use, and start off we can calculate the angle is the inverse tangent of the y value. For the violet, that would be 40 centimeters divided by the spacing to the screen, which is 100 centimeters. And if you do that calculation, you'll get a result of about 21.8 degrees. Then you can use that to calculate the wavelength. The wavelength for the violet end is going to be d times the sine of that angle. And d is 1 times 10 to the minus 6 meters, or about a micron. And if you do that calculation, you'll get a reading of about 371 nanometers, which is very good because the lab manual suggests you should only be able to see out to about 390 nanometers on that violet violet end of the spectrum, and because we were using the reflection off of the whiteboard, our eyes were actually able to see down to 370 nanometers, which is remarkably good. And for the red, if you go through the same calculation, I got a wavelength for the red of 721 nanometers, which is almost exactly where the text says we should be able to get down to 720. Again, looking at the reflection off the white was very helpful and a nice trick that we learned in this lab. So that concludes Laboratory 1-5B, interference and diffraction, and I hope you've learned a whole lot about that and will be able to use these kinds of skills in your photonics careers and in the future of fundamentals of light and lasers. We'll see you next time.